Um, Welcome everyone to AAC's midweek KSS by our very own president Aditi Marathe. We'll be speaking on the recent magnetar explosions that happened and the origin of fast radio bursts. Please keep your mics and videos off so that we don't waste bandwidth, and keep your questions to the end when the speaker finishes their talk so that they can answer them all at once. So, without any further ado, Aditi, please.
Okay, cool. I'll start. Okay, thank you for the introduction, first of all, Samarth. Yeah, so I'm Aditi, and today I'll be talking first. There will be kind of a precursor to the recent burst, as Samarth said about the SGR. So first, we need to know what these bursts are in the first place, and then we can uh, go deep into the SDR burst that recently happened. All right. So first, let me start with fast radio bursts and what they are. Okay. So fast radio bursts. So F stands for fast. So they obviously have some temporal relation with them, associated with them. So fast here tells us that the burst lasts for a few milliseconds at the max. Okay, there is someone who wants to join in, and I will have to do this at time. Okay, this is bad. Okay, so I'll continue. F is for fast, and these fast radio bursts usually last for a few milliseconds at the most. Like, this is the upper limit to them. And then R stands for radio, obviously. So these have wavelengths of about a few meters. All right. So that's basically all that we can gather up on from the name itself. So let's go into how we first, yeah. So why is so much importance given to fast radio bursts by the scientific community? Okay. So let's first go into when they were first discovered. They were first discovered by Duncan Lorimer and his student David Narkevic in 2007, when they were looking through some archival pulsar survey data. So if you know uh, what are pulsars, so pulsars are basically pulsating signals that we get from, well, pulsars. These are also in radio band, but the only difference between FRBs and uh, pulsars is that the radio signal that we get from pulsar is very periodic, while FRBs are just random bursts in radio frequency, which are very short. Okay, so why are FRBs so special? I mean, what is so special about them? So first of all, these bursts were found. Okay. First of all, these bursts were found only in the radio band, and usually whenever a burst happens anywhere, we see the burst ranging in a pretty much, we can say, at least wide range of the electromagnetic spectrum, right? So if there is something in radio, we can usually see something in optical or maybe UV or something, right? But these bursts were very specific to radio wavelengths, and that's what actually mystified them even further. So we couldn't see any other counterparts in any other in any other part of the electromagnetic spectrum, right? So the other thing that also made them so special was their extragalactic origin. So these bursts were found to be from not from our Milky Way, some other galaxies, right? And how we found out this will be explained in the next slide. which is through a parameter that is called a dispersion measure, right? So these are some basic parameters that we need to know before we go further, right? Because we are just making claims here that, yeah, the origin of this water FRBs is extragalactic. But how do you know that it's extragalactic? How did you measure the distance? I think Rakshit took an extensive cases dedicated to measuring distances. This is just one small part of it. Yeah. Then there are polarized FRBs, right? What do you mean by polarization? Does anyone know what is polarization? So these signals that I got from the FRB were extremely polarized, which means that the electromagnetic waves were very directional. So, so if you guys, how can I explain this? Okay, I think I won't go into the details of polarization right now. But there are two types of polarization vaguely. I can broadly circular polarization and linear polarization. Again, I don't want to go into the details of this, but yeah, what is the important conclusion that we need to take away from this is that electromagnetic waves were extremely polarized, which indicate that their origin was from a very strong magnetic field. All right. Okay. So coming back to the point of their extragalactic origin, so almost all of these FRBs that were detected, I think about 30 of them, not more, much, right, for to analyze any scientific data extensively. So about 30 of them were detected, and most of them were had extragalactic origin. So how do you know that any source has extragalactic origin? This comes from the dispersion measure. Right. So the dispersion measure is, if I go to my previous slide, you can say roughly that it is the slope of this pulse here, right? So on the x-axis, you say you have time, and on this left hand, y-axis, you say you have frequency. So this slope is roughly what is the dispersion measure. Dispersion measure is like an indirect and accurate method to estimate the distance of the source of the source. But first of all, what is dispersion measure? So if you look at this figure closely, you can see that the higher frequency signal arrives first and the lower frequency signal arrives later. Right? So there is this dispersion that occurs in intergalactic medium. This dispersion is due to the uh, charged particles that are present, like electrons or protons. And these charged particles slow down the lower frequency electromagnetic waves more than the faster, than the electromagnetic waves with higher frequency, right? So then you get this slope of pulse, right? So naturally, we can say that this dispersion measure is dependent on the number of charged particles that are there between any 2 points, say the source and us on the earth who are observing, right? So what we have is electron density, right? Mean electron density, I would say. And that multiplied by the distance basically gives you the dispersion measure. So this distance d is the distance between the source and the observer, right? Okay. So you know what dispersion measure of the signal is. because you observed the signal, right? You know what the mean electron density is. You divide the dispersion measure with the mean electron density, you get the distance d. Right? So that's how we got the distance of these FRBs, and we concluded that these FRBs have, well, extragalactic origin. And but there are obviously certain inconsistencies that one can point out in this way of measure the distance, which is the first one comes to mind, that we just assume mean electron density, which can obviously not be true. We can have maybe our source has some cloud around it, some dense cloud of charged particles around it, maybe, or there is some random cloud of charged particles in between. So in which case, obviously, we are overestimating the distance if our assumed mean electron density is actually lower than what the distance, right? So yeah, these assumptions are there in this way of finding out the distance, but yeah, let's just oversee these right now and assume that yeah, we are almost surrounded by a homogeneous cloud of electrons or charged particles. All right, and yeah, okay, fine. Now we know that these are mostly have extragalactic origin, and yeah, these two are, and only radio spectrum, right? So these two things are what we know about fast radio bursts till now. Okay, but question was still there. What is the origin of these fast radio bursts? So there were multiple theories for fast radio bursts, which ranged from, well, black holes to magnetars to extraterrestrial life, obviously. But none of these theories were proven to be right, because there was no substantial evidence to support or disqualify any one of them. All right. So that's when the recent SDR burst comes in. Okay, first of all, again, what is SDR? What are these random numbers? 1935, 2154. What is this? Okay, I'll tell that. So SDR stands for soft gamma repeater. And the numbers that you see, 1935 and 2154, is basically the right ascension and declination of this particular soft gamma repeater. So there are about 7 soft gamma repeaters that we know till now, and 1935 plus 2154 is one of them. So 19 degrees 35 minutes plus 21 hours 54 minutes is the are the coordinates of this particular soft gamma repeater. I hope you guys are familiar with this convention of right ascension and declination. If you are not, Google it, please. Okay, so yeah, coming to this soft gamma repeater again. Astronomers obviously give the obvious names: neutron star, magnetar, pulsar. This is one of the such typical example, soft gamma repeaters. So yeah, actually soft shouldn't be there, but okay. So soft gamma repeaters, now we are coming to the other end of the electromagnetic spectrum, right? So till now we are talking about FRBs, which are in the longer wavelength, lower energy part of the electromagnetic spectrum, but gamma rays are the exact opposite. They are lower wavelength and higher energy electromagnetic waves, right? So then we have So these summer repeaters obviously give out random signals in the gamma ray spectrum of the electromagnetic waves, and their origin is known to be a magnetar. Right? We know that these SGRs are magnetars, right? Uh, so the bursts coming out from these SGRs are broadly classified into three types. One are short bursts, the other are giant flares, and then you have intermediate bursts. So these three types are classified on the basis of two things. Obviously, uh, temporal classification. So short bursts are very short, which last for about less than 2 seconds. Giant flares are something which lasts for more than hundreds of seconds, and intermediate bursts are between both of these. These bursts are also have this same classification in terms of energy. So short bursts usually have energy of the order of, I'm not sure, of the order of some 10 raised to 42 ergs something. Giant flares are the order 10 raised to 46, and then intermediate bursts are of the order of 10 raised to 42 to 44-ish. So this particular soft gamma ray repeater was discovered on 5th July in 2014 through a series of three short bursts detected by Swift BAT. So Swift is another mission which it's a space telescope which observes gamma rays mostly. At least Swift BAT observes gamma ray bursts, like high energy spectrum bursts, right? And then we also know that it is at a distance of 9.1 kiloparsec. So, okay, so do you guys know what parsec is? Okay, I'll just give. So, one parsec is 3.2 light years, right? So, uh, yeah, won't go into the details of what parsec is. It's just parallax of an arc second, but okay, not going into that. Moving on. Okay, so what was new with this recent burst activity? Okay, so this recent burst activity was first detected by Swift BAT, as I said. So this flare was detected on 27th April 2020. And obviously, a Swift BAT is something which detects bursts in higher energies. So this was a gamma ray detection. Just a second. Then on 28th of April 2020, there was CHIME. So, CHIME is a telescope which observes in the radio band. So, it confirmed two bright radio bursts, which happened on 27th April, but confirmed them on 28th. So, SwiftBat has rather a very dynamic system of reporting gamma ray bursts, but well, CHIME takes some time to process and then report fast radio bursts. Right? So on 28th April, CHIME reported two bright radio bursts, which coincided with the time of the bursts that were detected by Swift or BAT. And whoa. So this is the first time that this has happened, that we have seen a fast radio burst detection along with some detection in some other part of the electromagnetic spectrum, in this case, the gamma ray spectrum or X-ray spectrum, right? So yeah, that's what everyone has been going crazy about, that now we can prove that the origin of these bursts is from, in this case, from magnetars, and hence the theory that it originates from a magnetar is proved, and everything else all the other theories like black hole or black hole collision or neutron star black hole collisions or anything else is well um, disqualified, right? Um, so I'll go to the next slide. Okay. Okay, so we basically till now had two theories in which had the hypothesis of FRB origin. Again, these theories I will be going much more into detail in the journal club meeting, but this is just to give some overview about what the paper would be about. So the paper would be about various theories that were proposed for the origin of these FRBs and how the recent uh, SDR detection well uh, qualified one of the theories out of me. All right. So there were many theories. Some I think around 17 of them, but we won't obviously talk about all of them because A, we don't have time. B, I am not much. Uh, yeah, so these are the two theories. BNS merger or BNS merger is binary neutron star merger. So neutron stars are again stars of neutrons, obviously. And it was proposed that when two neutron stars coalesce or well collide, we have a FRB event. But then what had happened that we estimated the number of well binary neutron star mergers that can happen, and that number actually came out to be too small compared to the number of FRB events that we had, right? So the any theory here which has to be qualified to be uh, has to justify our physical observations, right? So we are observing way too many fast radio bursts that could have been explained by binary neutron star mergers, right? And then there was again the theory, the neutron star black hole merger. Again, this theory was discarded for the same reasons. We know approximately how many neutron star black hole mergers can happen, and then number of these mergers was way too less than the number of the fast radio bursts that we were observing, right? So again, this theory was also disqualified. Again, this is just an overview. Uh, that was just a brief introduction to what are fast radio standards, what is soft what are SDRs, what was the significance of the recent SDR burst, and so on. Right? So that's it from my side. Is there any doubt?
Okay, then Rakshit asks, what are soft gamma rays? Aditi?
So they are basically okay. So soft and hard is again maybe you might have heard this in X-rays as well. So soft gamma rays is basically the lower energy part of gamma rays again, and so I had written there X-rays and gamma rays, right? So it is the transition area between X-rays and gamma rays. So the harder X-rays and softer gamma rays. Does that answer your question? Um, ET, what? There was some question on ET. Okay, magnetars. Okay, so, okay. Samad, you want to answer this question? What are magnetars?
Magnetars are what? Stars with massive magnetic fields, I guess. Is that it? Neutron stars with massive magnetic fields.
Yeah.
Yeah.
Yes. Yes.
So I've
So,
heard that if they stay near if a magnetar is at the moon, moon's distance from the Earth. Every credit card on the Earth will be wiped. So that's how powerful the magnetic field is.
Yeah. So they are just neutron stars with extremely powerful magnetic fields. Right. So neutron stars can be pulsars, they can be quasars, or well, magnetars. Uh, they are composed of well the same thing, neutrons, but the amount of magnetic field or whatever other thing that dominates gives them their specific name. Somewhere I read that they can possibly be ET, right?